So when we said alpha 0.02, we just didn't know whether or not to reject without knowing the actual p-value. Okay, so if we made a 95% confidence interval, would the confidence interval contain 0? Our answer is?
Nope.
No. Okay, because here we found a significant difference, so that means we should have the same conclusion with our confidence interval. This was a 95% confidence interval corresponds to alpha 0.05. So we found a significant difference there. So to find a significant difference with the confidence interval, that means the confidence interval does not contain 0. Okay. So we have a significant difference. So the confidence interval will not contain 0. Okay, what about a 99% confidence interval? Will that contain 0 or not contain 0? Same data. Yeah, the answer here is we do not know. Okay? Because this corresponds to using alpha equal to 0.01, right? And at alpha 0.01, we don't know whether or not we've rejected the null. Okay? Alpha 0.01, we do not know if the p-value is less than alpha. Okay, so likewise, we do not know if the CI confidence interval contains 0. So study this example, or these problems here. Make sure you understand them, because you'll see similar questions on the quiz next week. Okay. I have to change our homework page around a tiny bit, but now I'm going to jump into just one section from Chapter 8, okay? So in Chapter 8, we're all about paired data, okay? And we're only going to just look at one section in Chapter 8 for paired data, and it's the t-tests for paired data. So in Chapter 7, we had independent samples. So that means we look at some sample of data over here, and we have another sample of data, and these two samples are not connected. Okay? This sample is independent of this sample. What happens in this sample has no influence on what happens in this sample. Okay? Paired data is just the opposite. The data in this sample is directly linked to the data in this sample. Okay? So my best example of paired data is before and after studies. Okay, so if we have, let's say we wanted to know, does a drug, so let's say some company said they have a miracle weight loss drug. Okay, you just take this pill, a week later you'll lose some weight. Okay. We want to know, does this thing actually work? Okay? And so what we would have to do is we would look at the before weight and the after weight and compare the difference here. Okay? So with paired data, the data in our two samples okay? And a key is that sample 1 and sample 2 must have the same n, okay? So here's an example. So let's say there's weight loss pill. You take the pill, you lose weight. That's what they claim, okay? Take the pill for, I don't know, 7 days. 7 days later, you would have lost weight. So, we'll have the before weight and the after weight. And let's say we look at 5 people, okay? Let's say before, this person weighed 220, this weighed 260, 170, 190, and 280, okay? And after, this guy weighs 117, this person weighs, no, not 117, I'm sorry, 217. 217, that would be ridiculous, okay. 256, 160, 167, 186, and 277. Okay. Do you think this pill works? Maybe, maybe not. Okay. All right. So I'm going to analyze this the wrong way. Okay. So do the analysis here with an independent t-test. Okay. So let me just punch these into the computer so I can calculate the sample 1 and sample 2. N1, N2, we both have 5 people, and I'm going to calculate Y and S, Y bar and S for each of these, okay? We have 220, 260, 170, 190, and 280. Is that what I got? Okay. Is 217, 256, 167, 186, and 277. Okay. Okay, so the mean of sample 1 is 224, and the standard deviation is 46.15. And then over here we have 220.6 and 46.14. So that is our data. So let's do it the wrong way. Okay? If we treat these as independent samples, wrong way is to treat them as independent samples. mu1 minus mu2 equals 0 versus the alternative that mu1 minus mu2. In this case, we want to know if the after weight is less than the before weight. So we would just do a directional test. Okay? So as independent samples, the observed difference is equal to 224 minus 220.6. I'm observing an average weight loss difference of 3.4 pounds. Is that statistically significant? That's what we want to know. Okay? Well, when we treat them as independent samples, we're saying basically, I got 5 random people, and we're seeing a huge standard deviation. Okay, so my test statistic is 3.4 divided by the standard error. The standard error would be the square root of 46.15 squared over n1, 5, plus 46.14 squared over n1, or n2, which is 5 over there, okay? And I get 29.2, okay? Just rounding up. So that's my standard error. So my test statistic would be equal to 3.4 divided by 29.2. I'm getting 0.116. And so when I look at my tail area, what do I have? I know my tail area is
15, 20?
Yeah, it's going to be more than 20%, but less than 50%. Okay, so even though the table doesn't have a 50% line, but we do know that our tail area is more than 20%. Okay, we could even just leave it as tail area is greater than 20%, just because it's assumed that it's, of course, always going to be less than 50%. Okay, so another. Oh, you know what? I forgot to do a directionality check. I'm sorry. But it does meet the directionality check, right? Because at least the average weight after the thing is less than the average weight before. Okay, so our directionality check is met, so that's why we are continuing on with the test. Okay, so we get a p-value over 20%. Is that okay? So our conclusion here would be what?
Not significant.
That the difference of 3.4 pounds is not significant. Okay? The difference of 3.4 pounds is not significant. And we would say we do not have evidence that, mu2 is less than mu1. Or we do not reject the null hypothesis. Any of these things. Okay. But I told you this is the wrong way of doing it. Yes?
So we have a test statistic of 0.116. I can't.
So here we would look up, we would do n1 plus n2 minus 2, and that would have 8 degrees of freedom. And you go to 8 degrees of freedom, that row and you're looking at 0.116, and you see 0.116 is smaller than that first number listed. That first number listed is 0.889. So the number that's closest to 0 is 0.889, and we're at 0.116, which is even closer to 0. So we know that the amount in the tail is going to be more than 20%. Okay, but this is the wrong way to do it, to treat it as independent samples, okay? Because what's going on here is we're saying, yeah, overall the difference, the average amount of weight loss is 3.4 pounds, but compared to the standard deviation or the variation that exists between starting weights, that difference is not significant. Okay? But if we take into account the starting weight and the after weight, we can treat these as paired samples, as we should. Okay? So this is the correct way. The correct way is we would create a third column called the difference column. Okay? And here we are not interested in the individual weights of what they started, but we are looking at just the difference. So we're going to do before minus after. So person number 1 lost 3 pounds, person number 2 lost 4, this person lost 3, this person lost 4, and this person lost 3 pounds. Okay. Okay, so the mean of the difference, okay, so I'm going to call this D bar. Mean of the difference is 3.4. And the standard deviation of the difference, let me do this. Is 0.548 or 0.5477. Okay. This is the standard deviation of our difference. And so we want to know, is our difference significant? Okay? And I think you guys can see that it will be, all right? So in our case, when we are doing when we treat it the correct way, as paired data, and this is an important distinction that I'm going to put up here. So for paired data, the null hypothesis is not about the means of the populations, but about the difference itself. Is the difference equal to 0 versus the alternative, the difference not equal to 0 greater than 0? In this case, because we're testing to see if the weight loss pill is effective, we want to see a difference that is greater than 0. Okay, so notice I'm not using mu1 minus mu2, I'm using D, where D represents the difference. Okay? Or I can use the same symbols, mu of the difference equals 0. Oops. And the alternative being mu of the difference greater than 0. Okay, so either of these. So write those down. So the mean of the difference, not the mean of the mu1 and mu2, but the mean of the difference. Okay? And so the test statistic would be the observed difference, what we observed, divided by the standard error. Okay? And so in this case, we're only looking at one column. Once I find the difference column, I ignore the before and after columns. I'm only looking at one column of data. So what is my n?
5.
My n is 5, okay, because I'm only looking at that one column of data. So my standard error is s of the difference divided by the square root of n. So I have 0.548 548 divided by the square root of 5. So my standard error is 548 divided by the square root of 5, 0.245. So my test statistic is equal to 3.4, my observed difference, divided by my standard error, 0.245. And I get a test statistic of 13.87. Okay, so this is ridiculously large. Okay, 13.87. We're about 14 standard deviations away from the mean. Okay. I would have degrees of freedom is equal to n minus 1. So 4 degrees of freedom. I go to the row 4 degrees of freedom. And what do I see? That my test statistic is beyond that last number there. So I know my tail area is what? Is really small. It's less than 0.0005. Okay, so we go to the t-table. And we conclude that our tail area is less than 0.0005. And that is my p-value. Okay, so my p-value is indeed less than 0.0005. So here we conclude what? To reject the null, and we have evidence that the average weight loss is greater than 0. Okay. So reject the null. We have evidence that the average weight loss is greater than 0. Okay. And that makes sense. If you look at the data table, if this truly is some miracle weight loss pill, you just take the pill for a week. At the end, it looked like everybody lost 3 or 4 pounds, okay, pretty consistently. And so that might not be significant, or it might not seem significant when you take into account the starting weights, but if consistently everyone's losing 3 to 4 pounds, just however this thing works, then it actually works, okay? Is that okay? All right, so that's the only section we're going to cover from Chapter 8, which covers paired data. All of Chapter 8 is on paired data, and this week I skipped 7:10, which I'll cover next week. Okay, so next week you have a quiz, and I'm going to have to update our homework page this week, so I'll update it tonight to reflect what's going to be on the quiz and the homework prompts that you need to do. Okay, so we'll see you guys next week.